Welcome to the Constructability of Avoided Two-Way Flat Slabs webinar. My name is Richard and I'll be your operator for today's call. At this time, all participants are in a listen-only mode. Later, we will conduct a question and answer session. Please note this conference is being recorded. I would now like to turn the call over to Mr. Mike Moda. You may begin.
Okay, Richard, thank you. Good afternoon or good morning, wherever you may be across this great country of ours. I'd like to welcome you to this webinar on voided flat plate slabs, design and constructability aspects. And I would like to start by thanking the American Society of Concrete Contractors for inviting me to do this webinar. As Richard said, my name is Mike Moda. I am the Vice President of Engineering for CRSI, the Concrete Reinforcing Steel Institute. A little bit about yours truly. Before I joined CRSI in 2008, I was with the Portland Cement Association for about 7 years as a regional engineer up in the Northeast. I am a member of ASE 7, the code committee, currently working on the 2016 version of ASE 7. I am also the chair of ACI 314. That's a committee on the simplified design of concrete buildings. And I'm a member of the board of the New York City ACI chapter. Okay, so the outline for today will start by giving a brief historical overview of voided slabs. I think this is important to put the topic in context. And then we talk about the new trends. After all, you know, there is a new mousetrap out there, and that's why we're here having this webinar. So what is it? And more importantly, you know, why is it important to you? So we'll talk about design and construction aspects and talk about case studies, 3 projects that are pretty much completed as we speak. The Perez Art Museum, Miami, Laban Arena at the University of Wisconsin-Madison, and the Harvey Mudd College in California. So the motivation for the seminar is, as you see on the screen, what are voided slabs? Why using voided slabs? I want to underline constructability aspects because for the seminar for the next hour or so, I really want to discuss how the system is built. More so, from an engineering standpoint, the system is fairly simple, but it's the constructability that I want to make sure that it comes across as something that it's not very difficult to do. And more importantly, why should it matter to you? After all, as a concrete contractor, you want to be able to self-perform. And, you know, this system, in my opinion, lends itself to that. So as you see on the screen, a couple of pictures of voided slabs, you know, for example, a waffle slab or a wide module, a one-way joist. So these systems have been around for a long time. And, you know, the goal is very simple. Remove the dead load, that extra mass from the slab where it's not needed to carry the load, so we can spend further. That is really, that's the challenge with casting place concrete, especially when it comes to promoting concrete in the office market arena, where more often than not, the knee-jerk reaction from architects and structural engineers is that structural steel is the system that should be used for office buildings. You know, here we have a system, as you see on the screen, a wide module waffle slabs obviously we can span 40, 45 feet. We're going to talk about the new system, new trends today that are another tool, if you will, in the toolbox that can be used to promote concrete in the office market arena. So why using voided slabs? Well, this is a game changer, as we'll see in a little bit. And again, we'll focus on constructability aspects, and hopefully you'll find that this system is very interesting, and you probably want to look more into it. So from a historical perspective, voided flat slabs, as I was able to find in the literature preparing for this presentation, there was an article published in Concrete International in May of 1983 by Bennett and Williams. And it was an article that discussed the use of these voided flat plate slabs for a project in Los Angeles. And so very briefly, it was a low-rise project, about 4 stories, 688,000 square feet, large unobstructed spans and heavy live loads, as you'll see here. So the system that they looked at was a one-way voided slab, the voids being created by the sonovoid tubes that you see on the screen. And again, the goal is very simple: remove that concrete where it's not needed to carry the load, so that we're able to spend further. This is a recurring topic that you'll hear me talk about today. They also did a study where they compared the voided flat plate system versus a precast double T as well as structural steel. So what you have on the screen, probably a little hard to read, but the vertical axis, if you will, is the cost increment in dollars per square foot. Across the bottom is the area in square feet. So you have two lines, 100 or base size. So for example, a 50-55 base size, obviously 2,500 square feet. So as you look at the trend of the costs across the base sizes, you will see that the voided flat plate is very economical as you almost reach a 2,500 square foot base size or 50 by 50. The double T eventually becomes a little less expensive. But for this project, obviously, the spans were in the 40-foot range. So they decided to go with it. Structural steel was not even close. And this was out on the West Coast. Obviously, in high seismic risk zones, removing mass is a benefit because it lowers the earthquake force demand on the structure. And so, as you can see, this is a system that's very appealing. It was back then, and it remains now, even in high seismic risk zones. Okay, so when the concrete is placed, the void is displaced, which creates buoyancy. Now, there's not enough mass in the reinforcement, the top mat of reinforcement, to hold the voids down. So there's two ways of doing this. We're going to see one way now that I have on the screen, and that's more of a positive, if you will, way of anchoring the voids using the straps. Let's see if I can use an arrow here to point to the straps. Okay, so you see here the clips that hold the straps under the formwork. So this way, when the concrete is placed, the voids are not displaced. That's one way. There was another way that I'll discuss in a little bit. But this is obviously key in the constructability of the system, because otherwise the system becomes buoyant. Other traditional systems, I mentioned waffle, wide modules, hollow core. That's another form of a voided slab. Foam voided systems, filigree. Many of you may be familiar with this. Very common in New Jersey area, and also in the Midwest in some areas. Essentially, for those of you who are not familiar, filigree is it's obviously a trade name. So I'll do my best to avoid talking about specific names and try to be general. But in this case, this is a composite where you have a precast panel that you'll see here on the bottom. And the precast panel is placed on the formwork, and it acts as a stay-in-place form, so it's directly placed on shoring. And then you have the voids, in this case, the styrofoam voids. They're placed, as you'll see there, again, with the objective to reduce dead load. And there's reinforcement that goes over it, and the cast-in-place stopping, and the system works as a unit when it's done. As you'll see, the surface is left rough to create, to have some composite action, some aggregate interlock. In addition to, there are some reinforcement trusses, wire trusses that stick out of the precast that you really can't see from that picture. But the whole system, in any event, works as a composite unit. So those are the traditional systems that have been around for, the better part of 50 years. And, even before that, there were other systems that used clay tile. But for the sake of time, I'm just going to leave it at that. So what is the new trends? The new trend with voided slabs. The goal is to use a flat plate analogy or a flat plate application, which is a system that requires very simple formwork, very economical in short spans for residential type buildings, The goal here is to use that same system with the simplicity of the flat plate formwork and be able to use it for longer spans, as you have in office buildings, 35, 40-foot spans. And so by reducing the mass here, we're able to span further and be competitive in that office market arena. So what you're looking at on the screen is you have the shoring here that is supporting the reinforcement, and is also supporting these wire modules, these cages, kind of hard to see, but they're in red, that house the voids. The voids are these blue balls, if you will, on the screen. They have to be placed inside these what I call position cages to hold them in place. These are very light. They're usually about 8 feet long. They can be easily placed across the bottom reinforcement. The position cage also works as a standee to support the top metal reinforcement. And it's a very simple system from an engineering standpoint, very similar to the design of a hybrid, if you will, between a flat plate and a waffle. We'll get into more about that in a little bit. But from a formwork, it's identical to a flat plate. No difference here. So the goal here is, how do you build this? Obviously, we have the same issue with buoyancy. By placing the concrete, we're displacing the void. So we need to be able to hold them down somehow. There's two ways. As I mentioned, the one before, it's more of a positive, if you will, way of anchoring the system, but it's time consuming. If you have a two-way slab here, you've got a lot of these voids. It's tedious, it's labor intensive to anchor all these systems in place. So what they've come up with, and this system, by the way, has been used in Europe for the past 15 years, is to place the concrete in two stages. The first placement, if you will, covers about 3 inches, so it'll cover about up to here, about a third of the slab. Okay, we let that set so that it's able to hold the cages in place. And so from that standpoint, it's very similar to the filigree, where we have, in this case, it's a cast in place because all the concrete is cast on site. But there was two concrete placements, if you will. And then, after 3-4 hours, once the concrete is hardened enough to hold the voids in place, then the second concrete placement can take place. And after that, the finishes are the same, vibration of the concrete and the finishes are the same as you would have with a conventional flat plate. The modules come in two sizes. The low profile for low profile spans, 4 to 7 inch thick, typically used for short spans. But what's really exciting about the system is these the standard modules, if you will, the 9 to 18 inch deep modules that are applicable to long spans. This is really this is the game changer here, folks, where we go in and can compete against structural steel in the office market arena. We can reduce as much as 30 to 100 pounds per square foot of the dead load. So it's a significant reduction in dead load that obviously helps in the design. 1 inch of concrete, normal weight concrete, is 12.5 pounds per square foot. We start reducing the slab, all of a sudden, the equivalent thickness. We still have the overall thickness of the slab. It could be even deeper than a conventional flat plate, but the equivalent thickness, if you will, is less for a longer span. So that's important to keep in mind. So in a cross section, I'll try to show the staging of the concrete, if you will. So at the top, we have the overall cross section before the concrete is placed, with the formwork at the bottom and the voids, as I showed before, on top. The first concrete staging takes place then by covering about a third of the slab, enough to anchor it and hold it in place. And then the rest of the concrete is finished, and that's it. And then the slab is finished in a conventional manner. Okay, so what are some of the benefits? Why are we doing this? Obviously, the goal here is to have large spans without beams. That's the key. Beams are expensive to shore, and in some states where labor is fairly inexpensive, okay, it may be a competitive system, but I can tell you, in the Northeast and Chicago and out west, labor can be expensive, and so eliminating beams is obviously a very cost-effective solution. Reducing dead load, that lowers the earthquake force demand on the structure, and this also has an important property which is relevant, especially when we talk about healthcare facilities, hospitals, where vibrations are a consideration. In addition to other types of facilities, rhythmic type facilities, health gymnasiums and things like that. Hospitals, healthcare facilities where the structure is very sensitive to high frequency vibrations. And without getting in the weeds with this, I can tell you that this system is very stiff and is very able to dampen the vibrations. And so some of the projects being used now actually have leveraged the ability of the system to be very, very good with vibrations. And so this is yet another property that important about this system. If we compare a voided flat plate, as you see on the top half of the screen, to a traditional structural steel system, as you see on the bottom, you'll see that the numbers are hard to see perhaps, but on the cast-in-place concrete, we have a 12-foot floor-to-floor dimension. The same thing with steel, but then the ceiling height in the concrete building is much, much higher than in the structural steel building. And that's because we're able to have a smaller cross-section than with structural steel. Because with structural steel, for a 40-foot span, you need at least a W27. You throw in a 5.5-inch concrete on metal deck, or even more than that, fireproofing, and all of a sudden you have a 3-foot just structural overall depth, in addition to whatever plenum space that you need for utilities. This is, again, economical overall to say floor-to-floor heights. That has other implications. It allows you to have additional floors given enough building height, or it can reduce the overall height of the structure with associated savings in reduced cladding costs, lower elevator costs, possibly even lower foundation costs. So all kinds of benefits associated with this. The system comes with two options, a cast-in-place, as I've been talking about, but there's also a precast, as you see on the right side of the screen, very similar to the filigree, where the panel comes in from a precast plant with the voids already in place. So all the contractor has to do is obviously set them in place on the shoring and cast the concrete. There is some additional reinforcement that needs to be placed over the joints, but that's the precast option. As you'll see on the left, the cast-in-place, the voids are placed directly on the reinforcement, and you'll see here the voids, in this case, the worker placing the voids. You also notice that the voids come in different colors, as I'm going to try to point out here. And this is because the voids are made of recycled plastic. So nothing is wasted here. And so from a sustainability standpoint, that has obviously benefits in that we're reusing plastic to make these voids. Site adaptability, another feature that obviously from conventional concrete, it's something that's a benefit. But even with this system, you can remove the voids to run fixtures, slab fixtures, as I'm going to show here. Run post-tensioning, bonded post-tensioning, or unbonded post-tensioning, as I'm showing on the right-hand side. So a lot of adaptability on site to accommodate site conditions, and the ability to use the system with post-tensioning. I cannot underscore that benefit as well, both as a bonded and unbonded system. post-tensioning. Couple that with reducing dead load, this really becomes a very, very effective structural system. Okay, so some of the design principles, and again, I'm not going to spend a lot of time on the engineering. I have a lot of pictures of the 3 projects that I'm going to spend time on, but very quickly so you get a feel for some of the design issues. The voids act like a solid flat plate, but because you have voids, obviously, we need to make some modifications. And the modifications come in 3 ways. The dead load, it's very clear we're reducing mass from the system, so we're reducing the dead load. The stiffness, again, because we're creating a void, we're reducing the moment of inertia, so we're reducing the stiffness a little bit. The important one here is the shear reduction. The shear has to be reduced by as much as 50 to 55% where the voids are. Now, here's where I need to make it very clear that much like a waffle slab, where the slab is solid around the column, and then you have the voids out in the middle of the bay. And the reason for that is because you need to have enough punching shear capacity around the column. You have the same system here. Around the column, the flat plate, if you will, is solid. And wherever the capacity of the reduced voided section, if you will, exceeds the shear demand. So wherever you have more capacity in the concrete, in the voids, versus the shear demand, then you can put in the voids. And if you have questions about this, I'm available at the end of the presentation to go over this in more detail if you'd like. You can use common design tools, analysis, finite element analysis, back of the envelope, all kinds of ways to do this, no different than designing a flat plate system from that standpoint, other than making these small modifications. I mentioned some of the cost savings that make the system really competitive, but here is a full list of additional savings. Obviously, reducing the lateral force, the lateral force requirements, especially in high seismic risk zones, can have benefits. Also, reducing the mass can have cost implications in walls, columns, foundations, all kinds of advantages. On the right-hand side, construction time gain. I mean, you're self-performing, even though there is another system here that may be perceived as, these cages. The projects that I've been involved with, the cages are available to the contractor, and the contractor installs them. So there's no issue from that standpoint. And I mentioned other advantages like reducing overall building height and associated energy savings with that, as well as retrofitting advantages. So let me jump in for the next 35 minutes or so and talk about the 3 projects that are under construction right now. Let me start with, this was the very first cast-in-place option of this system, the voided slab. There have been others that use the precast option, but let's start with this one. This is the Perez Art Museum in Miami, right on Biscayne Bay. It's being completed as we talk. At least the concrete is topped off, and they're moving on to the finishes and other things. So here's an aerial view of the structure. It's, as you see, it's a low-rise structure, about 4 stories, but it's a complicated building. From what I understand from the design team, structural engineer, the architect, numerous schemes were looked at, were considered, 30 to 40 different types of schemes, including structural steel. And they eventually settled on the voided flat plate option, which gave them the ability to design the large gallerias, as I'll show you in a little bit. Obviously, this being a museum, large gallerias were an issue. So what I'm going to show you for the next few slides is a construction sequence to try to illustrate how the building was constructed and why some of the portions of the structure were designed the way they were, because I think it'll make sense once it's done. So starting at the base of the building with the columns for the first floor, adding the first floor system on top of that. And so now you start seeing something that is becoming apparent, which are these boxes. And I'm going to point out to one. So these boxes here house galleries. And the goal here is to build a box that acts as one system with the floor. So you need to be able to tie the floor with upturned beams, tie them into the walls, and put another box on top. And by doing this, you're able to create a very stiff system that really works as a unit when it's built. So this box concept allowed them to have these large openings, as we'll see in a little bit. So continuing with the erection sequence here, the second level, more boxes on top of that. And you will see, I'm going to try to point out here, very large cantilevers here, and you're able to do this by having one box built on top of the box below. By doing this, you're able to remove some of the exterior supports and have these unobstructed views and these large cantilevers. So you'll see the boxes throughout the structure. The third floor slab and more boxes on top of that. And then we're kind of winding up to the very top where they had these precast beams just for architectural features of the structure. So that's the overall construction sequence very quickly. A cross section here shows a gallery and shows that this box concept with a very large cantilever here to the right-hand side with upturned beams, and I'm going to try to point out an upturned beam here. So there's an upturned beam here that works with the wall above to create a unit. There is also upturned beams in the middle of the slab that create, by upturning that beam and creating a false floor, if you will, you're able to have a flat plate formwork below that. And again, having the advantages of the flat plate formwork. But by doing this, you're able to have these large spans. So I'll show on the third level the upturned beam here, but below that you have a large span, or at least the illusion of a large span. This box here, again, a lot of arrows here. This box is being suspended in different ways. But in order to be able to achieve this, you have to reduce the dead load as much as possible. And this was the challenge, that why they went over a lot of systems was to be able to create this illusion of these large, some of these spans are as much as 90 feet. By reducing the mass, you were able to put a beam here, relatively shallow beam that was able to be placed inside the false floor with a raised floor above. And give this long span that the architect was looking for. So the ability to reduce the mass here was the key that made this to go cast in place concrete. Okay, so I'm going to show you some pictures now of the project during construction. You'll see off to the right the voids stacked and ready to be placed. The reinforcement, I'm going to try to show you here the upturned beams. You have one here. Oh, there is another one here. And so the reinforcement is placed for this, and there is another upturned beam here, okay, as you saw in the cross-section. And the voids will go in between this upturned beam in the slab, and the concrete is cast. You'll see here the work is carrying the voids. These things are very light, as I mentioned, so they're able to carry, you can easily pick up two on each hand and just set them in place. Here's a view of, again, the voids being set in place. It's important to make sure that they were separated to be able to place the concrete. So I think I have a better picture next that shows. So they used a very sophisticated system to make sure that the positioning cages were positioned at equal distance. This piece of wood here with a couple of grooves. But it works, and as you can see, they were able to place these voids in a consistent manner, and that did the trick. And they use different type voids. You'll see here these are larger spherical voids, and some of these reached, I don't know, 21 to 24 inches in diameter. Depending on the application, they use the squat voids, as I showed before, the normal size, and they pretty much use the full gamut here that's available. Here's a picture of at least one stage of the concrete placement. This one is ready to place the second to top off the slab. Similar picture here with the concrete done in the first third. This is hard to see a lot of information, but it's a drawing, obviously, that shows in plan where the voids are, and some cross sections that show how the voids work together with the slab. And you'll see the darker areas here that show how much of the slab has to be placed to anchor the voids. A little bit on the project from an outside. Obviously, this being a museum, so finishes were a must. There was a Swiss architect, and as you can see here, the concrete was finished on the outside, but they wanted to have this rough surface. Although the texture, looks very nice from a distance, but if you look close up, the texture was actually created using a jackhammer. So they jackhammer the entire side of the concrete wall to create that surface. And in addition to having these recesses in the slab, as you'll see here from an architectural feature, these were used for different purposes, to house sprinklers, to hide the lights. But as you can imagine, when you have a recess in the slab, something has to give on the other side of the slab, and obviously the reinforcement has to be wrapped around the recess, and that created a little bit of an issue with the placement of the voids. But then again, by reducing the mass and having the flexibility of the voids, they were able to do this, very efficiently. Just a few more pictures on this project, shoring in place here. Let's see. So you'll see the large cantilevers. Which is a feature of this project. Is really an interesting. Again, more pictures of the building and the construction. Here, getting up to the upper floors, you'll see here that the voids are covered. You have the upturned beams here, and the voids are in the middle of the slab here. And some of these slabs have an aspect ratio of 1:1, fairly square. Some of them are more rectangular in nature. So the combination of, obviously, the more square, the better of a two-way load transfer. The more rectangle, more of a one-way load transfer. And this is a rendering of what the building will look like when it's finished, which is, I believe, sometime in 2014. Okay, moving on to the next project, the University of Wisconsin at the Laban Arena in Madison, Wisconsin. This was the second system that I'm aware of, or the second project, rather, where the voided flat plate system was used. And so the voids were used in this particular section here that spans over the locker rooms. And the reason they used the voids here was to reduce, again, by reducing the mass, they were able to, in this case, keeping the same spans, but reducing the overall floor depth. So yet another way to, to create a different mousetrap here, if you will. keeping the same span, reducing the dead load, you can have a thinner slab profile that gives you additional floor to ceiling height in the locker room, which is what they needed. So that's why they use the voids here. These were precast, so the slab and the voids were done at the bottom third of the slab, and the voids were done at a precast facility off-site. You'll see here the voids housed in position cages, very similar to the cast in place, but again, done off-site. And you'll see here the voids are being placed on, being ready to be placed on the slab. You'll see here the concrete on the bottom, okay, and the voids right there. I know it's hard to see, but the system, you got some stud rails here to be placed around, obviously to augment punching shear around the column. You have the shoring at the site ready to receive the panels. The panels are delivered on truck and hoisted to the job, to the site, placed, hoisted in place on the shoring. And you'll see here that obviously about a third, I would say maybe a quarter of the slab is been placed, and the voids are above, housed in these cages. So when you top off the slab, these units don't move. This is looking from the underside of the slab, obviously using this type of a precast panel as a stay-in-place form. There's no need to reshore the slab. So that's an advantage, certainly, from using a precast option. And you'll see, if you look closely, you'll see a little bit of a grid pattern, which is the shadowing that's created by, as the concrete goes around the reinforcement, creates a little bit of that shadowing effect that you see there. So that's all you're looking at. Here is the joint between the panels. You see a little bit of daylight. More panels being put in place. You'll see the workers here standing on, let's see, well, arrow is not working, but you see the workers standing on these cages. So they're stout enough to hold workers in place. And something to point out here, let's see, what's my arrow? Okay. So around the columns, and there's a column here, obviously, as I mentioned before, the voids are left out so that you can have a full cross-section of concrete. In addition to that, you'll see the stud rails that we saw in the pictures before. And again, these further augment the punching shear capacity. So you definitely, you don't need to use a slab drop, as, you would have to without having to have this additional shear reinforcement. Obviously, there is benefits in doing that because you're saving a little bit in the formwork. Here's a close-up of the panels before the second placing of the concrete. Some reinforcement covering the joint here, okay, additional bottom reinforcement and top reinforcement over the joint. And this is a view with the, before the top concrete placement is done, before the slab is topped off. But obviously you see these areas where the concrete is being left out around the columns. So that, again, you can have additional punching shear capacity. You finish the slab in a very similar fashion as you would with a conventional flat plate, so nothing new from that standpoint. And here you see the slab being finished across the top to the bottom, the concrete being pumped. And here's the finished slab. And once you remove the shoring, you can't tell from below or above that there is voids in this slab. It looks the same way. So why were voided slabs used for this project? Again, approximate numbers without, getting too involved in specific dollar amounts, but approximately savings of $2 a square foot, about about 174 cubic yards of concrete. They saved about 3 days off the schedule, obviously saving on shoring by using a stay-in-place form system, and saved overall structural depth. Okay, the next project that I have is the Harvey Mudd College Teaching and Learning Building in Claremont, California. And so this is obviously in a high seismic risk zone. Here is a BIM model of the showing the project. Let's see, 4-story educational facility, about 80,000 square feet of voided slab. Not a tremendous amount of voided slab, but certainly as we are taking small steps, I almost like to make sure that we do the small buildings, we do them properly before we venture into, the large, 400,000 or 500,000, a million square feet of building space. So far, so good. As you can see here, different void sections were used, ranging from 9 to 20 inches. Overall slab thicknesses with obviously the domes inside the voids for the particular slab thickness, and again located in high seismic risk zone. Here you see again this was a precast option similar to what you saw before, just now with the University of Wisconsin project, where they brought in the precast panel and finished the slab on site. So aerial view of the project going up, and here's a close-up showing the voids. And you'll notice that in some areas the voids are left out. Okay, so if you have utilities or things like that, you can remove the voids without affecting the the structural integrity of the slab. Here's a close-up of the void. This is a picture around the column. So here are the stud rails for punching shear. This happens to be right over a panel joint. But again, once the system is finished, this acts as a two-way system. So it's, for all intensive purposes, it's a flat plate system. Okay, here's the same project, and they also used it for ramps around the parking garage. Here's the panel being put in place. You'll notice here there are some areas that are shaded differently on the picture, and these are knockoff areas for utilities, so that they can run utilities through these areas. So the section of the slab here can be knocked off and for utility purposes. Going back to the plant, you have the format for the slab before the slab is cast, with the areas where the openings are going to be located. And here is a close-up of the system before the concrete goes, and so you'll see here running the conduit between the voids. So, as you can see, a flexible system. Why was the voided slab again used for this? High visible exposed concrete ceilings, a lot of MEP coordination with this project. Really, reducing mass from a seismic standpoint was a driving force here, this being in California. Long-term deflection considerations were an issue as well. It saved about 750 cubic yards of concrete. Now, I want to make a point here that when I promote this system, and I've been promoting this system for the past 5 years, I go after a market segment where reinforced concrete is not traditionally the system that's commonly used. And I'm referring to the office building market. As I mentioned at the start of the presentation, the knee-jerk reaction is to use structural steel. So what we're doing here is going into a market segment where concrete is not commonly used. So what I'm trying to say is I'm not trying to cannibalize what we already have, which are the residential buildings, the short span buildings. I don't believe that this system is if economical for short spans, in my opinion, and the projects that have been done kind of confirm that you need to be at least in the 35-foot span range in order for the system to be economical. You certainly can do it in shorter spans, but an 8-inch flat plate is a very, very common system, a very economical system that is used for residential structures all over the country. Okay. I think I'll wrap up the presentation with the Watertown Regional Medical Center in Watertown, Wisconsin. This is the fourth project where, I guess I stand corrected from the original outline. I apologize. There's one more project here. This was obviously original medical facility, 2-story, 30,000 square feet, so not a very large structure. Existing concrete systems that were looked at, waffle slabs, concrete pan joist, precast concrete and steel beams. And I'm not saying, folks, that voided slabs are the answer to everything. By no means I'm saying that. What I'd like you to think of what you've just seen with these voids is yet another solution that we can put in front of the owner, the developer, the architect, the structural engineer, the decision makers, if you will, that there is a game changer here that should be looked at initially, not as an afterthought, because it's always difficult to try to convert a design that has been done in structural steel to try to convert that to concrete. There's obviously a certain amount of inertia from the structural engineer and the architect in trying to do that, as well as the additional design costs. The goal here, and some of the contractors that I've spoken to from the Midwest, the East Coast to the Midwest, and even out on the West Coast, we need to get in early on in the design process so that we can be effective in making these changes, in converting these projects from structural steel to reinforced concrete. So anyway, getting back on track with this, certainly the factors, the grid layout, the story height were issues that had to be considered. But again, the voided slabs came out on top here, and as you'll see, you're seeing the same type of pictures that I've showed you before. But what I'm trying to do here is show you that if you're going to do this, you're not going to be a pioneer. You know what happens to pioneers, right? They get arrows in the back. So somebody else has done this in the U.S., so there's a little bit of a track record that we can point to. And so that's the reason I'm showing you all these projects. Here's a close-up at a joint between panels. The concrete here being placed on the top half of the screen. And again, the voids in the middle, around the column being left out. And this was an addition that had to match the existing facility that I'm showing here. So they from a floor-to-floor height, they absolutely had to match the existing finished floor elevation. So the voids allow them to be able to do that by reducing the slab, having more control over the slab thickness. Why voided slab for the Watertown Regional Medical Center? Flexible and larger column grid, a thin structural system that led to higher headroom for mechanical, electrical, plumbing, as well as medical systems, material savings, increased construction speed by minimizing on-site labor. And, in summary, I'd just like to leave you with a thought. Certainly more information at our website, the crsi.org website. And just some concluding thoughts here. Voided slabs are a time-tested concept. From the turn of the 20th century to now, there have been many systems that have been used, as I mentioned, that range from the old clay tile systems to now to what I just showed you now. Different mousetraps, folks, to try to solve one problem, which is reduce the mass so you can span longer. That's the key. The technological advancements have improved efficiency. Certainly, it's a more sustainable type of construction by reusing plastic. Economical for commercial type structures. There are some design build advantages where you have more control, you self-perform, etc. And several new projects in addition to the projects we've discussed. I am aware of about 3 new projects that are in the works in New York City, a very large project in Iowa. Very exciting, folks. The system is here. I have been promoting and writing about this for the past 5 years, as I mentioned, and I never get tired about talking about voided slabs because I think, especially with this new improvement that we have in a very old technology. So I'm going to leave it at that. I think this is the last slide, and so it's about 4:52. I'm available to answer questions. I can stay as long as you'd like to answer your questions. So I guess I'll turn this over to Richard, and we can open it up for Q&A.
Thank you, Mike. We will now begin the question and answer session. If you have a question, please press 0, then 1 on your touch-tone phone. If you wish to be removed from the queue, please press 0, then 2. If you're using a speakerphone, you may need to pick up the handset first before pressing the numbers. Once again, if there are any questions, please press 0, then 1 on your touch-tone phone. Standing by for questions. Our first question online comes from Mr. Bob Jensick. Please go ahead.
Question was, how do the mechanical, electrical, and plumbing and sprinkler contractors view the voids in the slabs as far as anchoring their work? And part 2 is, do you guys do design assist to get the engineering community to warm up to the concept?
Excellent questions, Bob. Okay, so let's start with the first one. How do the MEP contractor looks at anchoring the voids? There is enough concrete under the voids, usually about 4 to 4.5 inches of concrete. That is enough to anchor. So, from that standpoint, I'm not aware of any issues. If you do happen to have an anchor that kind of falls in a void, and you need to, you may need to inject the void with grout or something to plug up that particular hole. But from what I've seen, most of the applications, there is enough concrete to anchor sprinkler lines and things like that in the 4.5 inches of concrete.
Okay.
The second question is, how do we help the? I hope that answers your first question, Bob.
Yes.
The second one, how do we help the engineering community? We are involved in several ways. On a direct project basis, when we find out that there's a project coming up that we believe should be a reinforced concrete project, if it's an office building, structural steel, we try to get in with the architect, the engineer, to talk to them about this. CRSI is actually in the process of finalizing a design guide on voided slabs. This will cover the architectural aspects, but primarily the engineering aspects of designing with voided slabs. And so, as I said, it'll be available in the next month. As the system is taking off, the timing couldn't be better to make this available to the design community. So, and the other ways I've helped, Bob, is I've written several articles that have been published in Concrete International, in Structure Magazine, and I've done many, many presentations around the country. This, by the way, is the first webinar on this topic.
Thank you.
You're welcome.
Our next question online comes from Mr. Richard Savasco. Please go ahead.
Thank you. Mike, I'm Rick Savasco. I'm with Seco Concrete Construction out of Cincinnati. Nice to meet you.
Hi. Nice meeting you.
I've got a couple questions. Has anybody ever done a direct cost comparison with this system and the wide module one-way joist systems that do many of the same things that it seems like this system does, with eliminating deep beams, reducing the dead load? It's good for vibrations. You can use post-tension systems with them. I'm just wondering how those how this system compares cost-wise directly with a wide module one-way joist?
Yeah, and that's a great question. I can tell you, and as I mentioned during the presentation, I don't believe that this particular solution is the answer to everything. Obviously, there is other cast-in-place systems that are very efficient, including wide modules. I don't believe a direct comparison has been done between the two to answer your question, only because, as I've shown you, as I discussed before, a lot of these projects have been converted from steel to concrete, and I'm not sure if in that process other systems like a wide module were, something that you would be involved with were used. To answer your question, I'm not aware of any. I'm not saying that they weren't done, but I'm not aware of any studies that have been done as a direct cost comparison. It would be interesting to see how they stack up. I can point you to one thing. CRSI has developed a what we call CRSI concept. So if you go to CRSI.org website, concept is a web-based system that engineers, architects, anybody can use. It's free to everyone. That looks at 6 different types of floor systems: a flat plate, a flat slab, a waffle, a wide module, a voided slab, and a voided slab. I think I covered all 6. And you can go in, again, at crsi.org. You can see concept. And concept allows you to, from a preliminary standpoint, play with these different types of floor systems, including the wide module, and you can compare the wide module to the voided slab, and you can compare it from, you have the ability to put in unit costs as well, so you can see how the cost stacks up. This is a software that meets ACI 318 design criteria. The modifications have been put in for the voided slab. So even though I'm not aware of anything that has been done for a particular project, I can tell you that concept will do the same thing, and you can go in and play with different spans, different loads, and see how it comes out.
Okay. Another question is, one thing that we've heard end users like a lot about the one-way joist wide module system is that there's invariably a need to put in penetrations through the floor slab some later time due to the modifications of the building. And with the one-way joist system, they have, they know where those joists are located, and they have a 4 to 5 to 6 foot space where they only have a 4.5 to 5 inch thick slab that they can make a core drilling through. How would you facilitate something like that with a voided slab?
No, absolutely. Obviously, that's a tremendous flexibility with a wide module. With the, I don't know if I can go back in. I guess I'll try to go back in. And just to point out again that you have a similar flexibility with this. And I'm trying to show a close up where you can see this, but. Because you cannot coordinate everything until you get to the job site and things come up and you need to make changes on a job site, you certainly have that flexibility with this to be able to do that. Again, I'm trying to see a picture that shows some of those openings. Maybe if I go back to this one. Sorry if I'm moving this a little too fast on your screen. Let's see. Well, okay. Maybe if I go back to this one here. There's some, you'll see, I'm trying to put a, there's an opening there. There's an opening here. So, or at least there was a void that was left out there for a particular reason. But anyway, those things can be accommodated on site. Granted, you do have a thicker slab that you got to cut through, so that's a consideration. Obviously, with a wide module, you have a 4.5 inch slab thickness between the beams that makes it more economical.
Right.
In concept,
regular.
Yeah.
Yeah.
I'm sorry.
I'm just saying that with the wide module, those areas where you can make the penetrations afterwards, are at very regular spacings. There's no guessing.
Absolutely.
Done. Yeah.
No, absolutely. It's certainly. Yeah. Go ahead.
I was going to say, do you know what the average cost of the material cost of the voids and the cages are?
I am not going to, not to try to evade your question, but I'm not going to get into costs only for two reasons. One, I really shouldn't, representing CRSI. That's not something I should do. Two, I can refer you to people that can inform you on that information. And three, we've only had, 4 projects in the works, so I don't think we have enough of a track record yet. They've been in different parts of the country, Florida, Midwest, West Coast. So I don't know if we have enough track record yet, but I can point you to 2 companies that deal with this. If you're interested, they can give you more information on that.
Okay. All right. We actually have one project.
Sorry,
I'm just saying we know of one that's going on right here locally, so it is very interesting.
Okay. Locally being where, if you don't mind me asking?
Dayton, Ohio.
Oh, you said, I'm sorry, Dayton, yes. You said, yes. Right. There is a project there that I'm aware of that is going at Wright State University.
Wright State, right, correct.
Yes. Okay. Well, thank you for your questions. You're welcome. Yep. Any other questions?
Again, that's 0, then 1 on your touch-tone phone. We have a question online from Mr. Robert Model. Please go ahead.
Hi, I'm with Wacker Noise Incorporation, and we make construction equipment, primarily trowels and finishing equipment in the group that I'm in. And my question relates to the effect on finishing, and obviously the huge variations in concrete thickness and how that affects bleed water and curing, and therefore troweling. Do you have any experience with that?
Well, from what I've heard from contractors that have done it, they don't see a difference, or at least not a difference that's noteworthy. But again, obviously, I don't have any personal experience with that. Just by and when I visited the Miami Art Museum, where they finished the trowel finished the slabs, this is not something that came up as a negative. Let me put it to you this way.
Okay. And then also, what about, especially on the slabs where you're bringing them in with the cured, I'll call it the cured underlayment, and then the voids and the cages, do you have any issues there, especially in the seismic regions with, I'll call it a cold joint there, when you've got that cured 4-inch thick base and then you're pouring additional concrete on top of it?
And that is an excellent question. And obviously, as you saw, the project was built in California in a high seismic risk zone. So you're talking about, first of all, concrete is very high, has a very high in-plane stiffness. And there is this steel reinforcement. These cages, they're made of steel reinforcement, even though they're not. That reinforcement is not used for shear calculations. Okay, it's just there as non-structural, if you will, but it's there. Inevitably, it's there, and it bridges the gap and it creates a composite action. So that is kind of a redundancy in the system, if you will, that is not leveraged from a structural standpoint, but it's there, and so. Very similar to the filigree, I'm not aware of any issues. Certainly there's a cold joint there, but there is enough composite action that this is not an issue.
Thank you.
You're welcome.
Once again, that's 0 and 1 on your touch-tone phone. And at this time, I'm showing no further questions.
Okay, Richard, thank you. And I'd like to take this opportunity again to thank the American Society of Concrete Contractors for inviting me to give this presentation, and thank everyone for listening and asking really excellent questions. Let me give you my email in case you have additional questions that you'd like to ask. It's mmota, at crsi.org. So MMOTA at crsi.org. And feel free to ask any questions you have, and I'll be more than happy to answer those. Thank you very much.
Thank you, ladies and gentlemen. This concludes today's conference. Thank you for participating. You may now disconnect. Speakers, please stand by for your post-conference.